In this video, we're going to talk about the acoustic properties of consonants, and our goal is really to think about our linguistic organizational principles that we learn from phonetics, and think about those linguistic features like manner, place of articulation, and voicing, and for each one of those, try to think about the acoustic signature, where you'd look in the waveform, where you'd look in the spectrogram, to identify the specific place, or whether something's voiced or voiceless, and so on. As opposed to vowels, consonants don't have just a simple formant structure, but they have other signs that we look for. And so we're going to go through a lot of those in this little video capsule today. And the goal here isn't so that you can look at a waveform or in a spectrogram and know exactly what it is that was spoken, but just to start to develop an intuition to say, oh, this is a stop consonant and not a fricative, or this definitely looks like a vowel, things like that. So let's start with just some of the basic cues. So what we have here is not speech, just some, modulated noises here. And what I want to draw your attention to is what I call the rise time. So how long does it take for the envelope of the sound to go from 0 up to full volume? And so what this does is give us a cue for how quickly the sound bursts out to be full intensity. So this will come back as we look at different manners of articulation. Another thing we see here is different modulations. So over on the left side here, we have a slower modulation rate, and then that gradually speeds up over the course of the sound. Another thing about modulation is that in addition to its speed, it can have different depths. So again, on the left here, we see modulations that go completely from full volume down to 0, but over toward the right, those modulations are pretty shallow. So just to get a sense of what these sound like, let's put some modulated sounds together. We can listen to these here. So that's a modulation rate of 4 per second. Now here's 6 per second. A little bit faster. And now twice that is 12 per second. This will be pretty fast. And even faster than that would be 20 per second. So those are different modulation rates. And then we can also change modulation depth. Oops. There we go here. We can open that sound. Here's full depth. Here's where some of that depth is made shallower. And as well as the sound of my phone hitting the floor. There we go. And here's really much more shallow depth. And over on the right is depth that's so shallow you might not even hear the modulation anymore. So what we want to do is start to think about how to connect those acoustic properties back to the linguistic properties. So in general, if you have a lot of vocal tract constriction, you're going to have greater modulation depth because you're actually completely stopping the airflow and then restarting it. So it should go all the way down to 0 and then back up to full intensity. Similarly, if you hold back the airflow and build up more and more pressure, then once you release it, it should come out with greater speed. And so maybe you should have a quicker rise time. So let's look at how that appears in actual words. So here we have the word bust, and there are a few things I want to point your attention to. So first, we have some areas of the sound where there's really pretty much just silence. And so this is obviously more visible if there's some sound before and after the silence, as we can see here between the S and the T release. Before the B, it's not really clear whether there's actual silence or whether the person just, didn't start speaking yet. So let's look at this as it appears in word medial position. So here we have aga and aka, okay, and we can see that silent gap is really part of how the sound is produced. And just to demonstrate that a little bit here, we can look at a word like risk. This here.
Risk.
And then if I make a copy of that sound and actually take out that gap, what we see would be this. We can actually take that gap, select it, just as you'd select like words on a document, and cut it. And here's what that would sound like.
Risk. Risk.
So you can still maybe understand the word, but it doesn't sound natural as it would as the original recording with that actual gap in it,
risk,
right? Risk. And here's the one with no gap.
risk,
So now it just sounds like a little noise added to the end of it. So those gaps are actually part of what it means to produce that sound. Here's another example of the word shack.
shack,
And then without the gap, it sounds like this,
shack, shack,
like it's been improperly spliced. Okay, so back to our stop sounds here. In addition to that gap, we also have evidence of a really rapid onset, which I'm highlighting here with our red arrows. So that's really a signature of a stop because we're holding the airflow back and then releasing it all at once. So we can look for a bunch of different stop properties using prot as a tool, right? So we can look at these stop sounds here. Here's a woman producing a few stop sounds.
Aba, apa, ada, ata, aga, aka.
So for all of these, we can see there's a gap in between the two ah sounds. So in between aba, there's that little gap there. And then in between ah and pa, there's a little gap there. So that's one of them. In addition, if we look at the D sound here, we can see that this onset is really almost instantaneous. In fact, we'd have to zoom way into it to see that it's basically a perfectly vertical line, which is one of the signatures of being a stop sound. For those of you who speak languages other than English, particularly if you speak an Arabic language, you'll notice that we have another one of those even before the first ah sound, which is a signature in English that we do when we have a vowel onset word, is we actually put what's called a glottal stop here, which sounds like this. That little sound is how we signify to the listener that the word begins with a vowel sound. So we have a bunch of stop sounds on the screen, and we can explore some properties such as the duration of how long we have, not just after the gap, but during this actual part of the sound that we can hear here, the t, that part is aperiodic, and we can count how much time has elapsed between the start of that and then the start of the vowel. So that's a distinctive signature of stop sounds as well that we call voice onset time. We'll have a whole video about this in the next capsule, so I won't spend too much time on it except just to point your attention to the fact that we'll actually want to be keeping track of some of these landmarks, like when does that burst happen and when does the vowel begin. This voice onset time is a really well-known and well-understood property of stop sounds that if you're going to understand any consonant feature, this is usually the one you start with. So we've been talking about stop sounds a lot, but there are lots of other consonants as well that we want to give some attention to. So now we're going to move on just to think about some other properties. And to do so, we want to start with some of the basic properties of acoustics, like the envelope, the fine structure, and so on. So you'll remember that different manners of articulation correspond to different amounts of airflow. And so because of that, the different manners that we see here, so we have a stop sound, a fricative, an affricate, another stop that's voiced, a lateral, and then a nasal sound. All of these have different ways that the airflow is shaped as it's coming out of the mouth. And so therefore they have different envelopes that correspond to those manners. So here, that was what we're getting into the differences in rise time. So here we have a fricative that has a longer and smoother amplitude rise time compared to, for example, a stop sound. So if we compare ta to sa, what we see in the envelope of ta is it has this silent period, the 0 mark, and then it immediately has a vertical line gaining some volume right there. But for the sa, it really gradually rises up to that volume. So that's one of the main differences between a stop sound and a fricative sound. An affricate is a bit of a combination of both, where you see a rapid onset, but then you see this prolonged period of noise that you can see in the spectrogram here. One of the things we think about is the differences between fricatives and affricates. So the main thing to think about, there are two main things. One is that the affricate will be shorter in duration, and this is one of the signatures of it being kind of like a stop sound. Stop sounds are pretty short, as well as we have a more rapid onset time for ch than we do for sh. So one of the things you can do is play with a recording of a sound, such as chip. Okay, I think we have that here. Well, we have the word ship. And so what we can do with this word
ship,
is if we take away some of the duration of the fricative sound. So I'm just going to cut this away. Now listen to what this sounds like.
chip, chip,
Now it just sounds like chip. So it's really the same sound. I've just blocked some of it out. And so this longer duration and longer onset of the sh sound, if we just make that shorter duration with a rapid onset, we can just turn it into a ch sound. Okay, so we can move on to another category of nasal sounds, and these are pretty tricky because they ask us to really think in some detail about both the waveform and the spectrogram. So let's look at a word, an example word here, like the word name. We have a nasal both at the beginning and the end of the word, and what I'm pointing at are the boundaries between where the nasal, in this case where the nasal ends, the vowel begins, and here where the vowel ends and the nasal begins. So we can see these cues in the waveform that we'll zoom into in just a bit. And what we want to think about is the lack of upper formant energy. What I mean by that is something that's visible on the spectrogram only. It's hard to see this on the waveform, but we'll touch on it. So we can see in this first area where the nasal is, we really only have low frequency energy, whereas for the vowel, for the A in name, we have a lot of this high frequency energy that comes in. And as soon as that vowel goes away and turns into the M, it kind of disappears. So if we zoom into this part, what we see is even on the waveform, we see a lot of extra detail in this high frequency fluctuation that corresponds to that high frequency energy in the spectrogram. That all goes away once it turns into the nasal, and now we just have this very smooth looking periodic pattern that really just corresponds to that that low frequency murmur of the nasal sound. If you're wondering why that happens, we can think about what happens to the airflow. So for an oral sound, right, the air just sort of comes out of the oral cavity. There's a lot of high frequencies that are there. But for the nasal sound, over there on the left, within the oral cavity, some of those high frequencies and that acoustic energy is just actually trapped in the mouth. Because if you produce an M, you're actually holding a closed resonating chamber in your mouth, but the rest of the airflow just sort of flows out smoothly through the nose. So for those of you who are interested in some of these extra details, what we're talking about are nasal anti-resonances. It's a little bit beyond the scope of this class right now, but this is just there for those of you who are really interested in this aspect of speech acoustics. Some more examples here of some nasals where we have a nasal part here at the beginning of num, then our vowel, then another nasal part. What we can see is that the nasal is lower energy overall because some of that energy is being stolen away, again, by the oral part of the vocal tract. We can see the same pattern in nudge, where that nasal is there, but it's not quite as intense as the vowel. Then this part looks a little bit like a nasal, but what we want to look at here is that this is so dramatically lower in intensity that it's actually just part of the j sound. So this part, before the j, and a nasal are very, very similar, and it's not really the scope of this class to always tell those things apart, but it's one of the things that we can notice. So the point from this slide, nasals have less high-frequency energy, and vowels have high-frequency energy in multiple formants that we can see in the spectrogram. Another thing you'll notice about this is that the nasals have different formant patterns here, and what this corresponds to are different shapes of the vocal tract. So just as we are changing the shape of, say, a bottle as we're making resonant frequencies, if we change the different shapes of the vocal tract, we'll see different patterns in the frequencies. So a cartoon sort of schematized version of this we can see here for the different places of articulation, b, d, and g. What we would see on a spectrogram are different patterns of where the highest energy frequencies would fall. So what we're looking at are the transitions into those horizontal lines. The horizontal lines all have different places, but what we want to look at is how they actually emerge. So for the B sound, all of those lines begin with an upstroke, okay? For the D, all of the first ones begin with an upstroke, but the second formant begins sort of at a target frequency, and depending on where it goes, it can either rise into it or it can fall down into it. And the third formant frequency always slides down into its position. Okay, so for the G sound, we're actually beginning with a pinched second and third formant. and then after that, it sort of goes into its steady state. So it's a little maybe easier to look at this on a cartoon version like this, but we actually do see these patterns in real spectrograms. So just to give you a taste of this, if we look at voiced stops like these, you can look at the spectrogram directly, or you can tell the computer to show you the formants. And now we can see, if we set the formants properly, which I'll try to do here, there we go, then we can see these patterns where the distinct pattern of that formant tracking in red really tells us that these sounds have different places of articulation. So notice, though, that if I turn the spectrogram off, these sounds are really hard to tell apart, because on the waveform, it's very hard to tell place of articulation. I would say it's nearly impossible. So from the time information on the waveform, that gives us information about manner of articulation and voicing, but to really understand place of articulation, what we're understanding is changes in resonant frequencies. And if it's frequency you want to look at, you want to see the spectrogram. Stops aren't the only sounds that have place of articulation. We can also see that in fricatives as well. So for a sh compared to a s sound, we can see on the spectrogram that sh has energy at a lower frequency and s has energy at a higher frequency. So even if these weren't labeled, if you see differences in the frequency content, you can be pretty sure that what we're looking at is a change in place of articulation. So let's go back to voicing just for a moment. As we're looking at different fricative sounds, we have a clear difference between sh and s here. The f and the theta sounds are so acoustically similar that it's very difficult to tell these apart. And for those of you who are interested, I can gladly field those questions later, but we won't really focus on that so much right now. What I want to draw your attention to is if we compare this voiceless series of sh, s, f, f to the corresponding voiced series of j, z, v, v, what we can see are a few differences in the spectrogram. So I'm going to toggle back and forth just for a moment, and then draw your attention to the fact that for the voiced sounds, we have what's called a voicing bar down here, which is just a bar of energy that corresponds to the lowest frequencies. That just really tells us that the sound is voiced. To compare them side by side, we have an S on the left, a Z on the right, and so there are two differences I want to draw your attention to here. The Z has a voicing bar down at the bottom, and Z also has periodicity in the waveform. As opposed to the random fluctuations in S, the Z has a more regular set of fluctuations that correspond to the rate of vocal fold vibration. The last set of sounds that we'll talk about are the liquid sounds. So a full description of this is so complicated that really goes beyond the scope of an introductory class. But the one thing I want you to know about this is that there's a particular acoustic signature for R sounds, which is a third formant. So let's go back to this real quick here. So what we have is the first formant, the second formant, the third formant, which is the one that has this little hook in it, and then the fourth formant way up there. So if we compare ra to la, they're very similar except for the fact that the third formant has a different shape. And when that third formant sort of sinks down really low, that's the signature of it being an R sound. So I'm highlighting it over on the right for lead, and then on the left for red, we can see how that third formant starts at a much lower frequency, and that's really the signature of the R in the spectrogram there. Going back here, we can also just remind ourselves that if all we had access to were the waveforms, this would not be a possible task. You actually really need to see the spectrogram to appreciate that formant difference there. So consonants can be R-colored and vowels can be R-colored as well. So if we have the vowel in the name Bert, this is what the spectrogram would look like. And it looks like it might only have 1, 2 formant frequencies, but we're actually looking at our 3 formant frequencies, where the third one sinks so low that it gets very close to the second formant. So if you talk to Bert, you should comment on how low his third formant is and how it makes his name R-colored. So just to recap here, voicing and stop consonants corresponds to voice onset time, which we can measure on the waveform. We'll have a whole video about that in the next segment. Voicing for other sounds, what we're looking at is low frequency energy, periodicity, and durational cues. Manner of articulation corresponds to changes in the amplitude envelope, with particularly fast rise times for stop sounds. Place of articulation corresponds to different frequency patterns, and a consonant feature of rhoticity corresponds to a low F3. There's a good website here which walks you along different waveforms and speech patterns, and one of the things I like about this is that it reminds you that as you're looking for specific patterns, you're limited by the exact graph that you're looking at. So for example, as we've pointed out a couple times in this video, waveforms can tell you that you're looking at a specific kind of sound, like a vowel or a stop sound, but they can't reliably tell you exactly which vowel you're seeing or exactly which stop consonant you're seeing. To get that exact knowledge, you have to look at multiple properties all at once, do some comparisons, and also remember that speech is variable person to person, and you have to be pretty experienced to get that level of detail. I'm not looking for any person in the class to demonstrate that level of expertise at this time, but just to demonstrate that we know that if we're looking for feature X, we look for property Y on the spectrogram or on the waveform, for example. Okay, so for the next set of lecture slides, it'll be in the next capsule here, we'll just focus specifically on voice onset time. That's the end for consonant features for today.